I'm Tim Ventura, and we're joined today by Dr. Daniel D. Stancil, the Alcoa Distinguished Professor Emeritus of Electrical and Computer Engineering at North Carolina State University and Executive Director of NC State's IBM Quantum Hub. Dr. Stancil earned his bachelor's degree in electrical engineering from Tennessee Technological University, followed by master's, engineer's, and doctoral degrees from MIT. He's a fellow of the IEEE, past president of the IEEE Magnetic Society, past president of the Electrical and Computer Engineering Department Heads Association, and his research has received an IR 100 Award and Photonics Circle of Excellence Award. He's also the author of 4 books: The Theory of Magnetostatic Waves, Spin Waves, Theory and Applications, Spin Waves, Problems and Solutions, and Principles of Superconducting Quantum Computers. So Daniel, welcome. It is an honor to have you with me. Thank you so much for your time today.
Thanks. It's a pleasure to be here.
So today we are focusing on an absolutely remarkable experiment that you did. This blew my mind when I read about it. I guess you did it back in 2012, and I just found this online. I actually read the article. I came back and reread it twice. I was like, this can't be real. And it was. You did it. It's amazing. You transmitted a coded digital message through solid rock using neutrinos. And on top of that, you have taken that research further since then into exotic communication using other types of particles. So let me start out with the neutrino experiment. What inspired you to explore communications technologies based on novel physics?
Well, thanks, Tim. One of my areas of research interest is radio waves and communications. And a number of years ago, a colleague told me about a hypothetical elementary particle called the axion. And one of the reasons that physicists are interested in axions is that they are a candidate for the missing dark matter in the galaxy. The reason why I was interested is that a physicist at the University of Florida, Pierre Schivi, showed that in the presence of a very strong magnetic field, axions could couple to radio waves and light. This meant that you might consider a communication system that starts out with radio waves or a laser beam, converts to axions to pass through the planet, then converts back to radio waves or a laser beam for detection. The only problem, of course, is that axions have not yet been shown to exist. And even if they do, it's likely that the coupling will be too weak to be useful. But that is how I got interested in communicating with novel physics.
Okay. And so the rubber met the proverbial road with neutrinos, and those are, again, an incredibly weakly interacting particle. I've done a lot of reading on that. It is amazing that you were able to do a detector for those. What I understand is that you used the Fermilab neutrino beam as a communications channel for that, right? So you started with the beam, and basically there was a sensitive detector several hundred miles away.
That's correct. What we used was, well, first of all, the way neutrinos came into the picture was that one of my former students, Jim Downey, who's at NASA, happened on the MINERvA website and looked at their capabilities, and he said, well, you know what, we may not be able to do this using axions, but maybe we could do it with neutrinos. So we approached the MINERvA team with the idea, and they agreed to collaborate with us. So the MINERvA project uses the neutrinos at main injector or NuMI beamline at Fermilab, and this creates one of the most intense neutrino beams in existence. Protons are accelerated to a very high energy, 120 giga electron volts, and then that's smashed into a carbon target. Subatomic charged particles called pions and kaons are then generated in the collision, and these are focused into a sharp beam using electromagnetic focusing horns. Pions dominate that collision process and decay into muon neutrinos as they travel down the decay pipe with helium to minimize the collisions. Undecayed particles are then absorbed, and the neutrinos continue on through dolomite bedrock to the MINERvA detector in the near detector hall that's about 1 kilometer away. The beam was pulsed every 2.2 seconds, and each pulse contained about 10 billion neutrinos. And on average, of those 10 billion neutrinos, on average, about 0.8 neutrinos were detected from each pulse. So that's how weakly they interact, as you pointed out.
Now, did the neutrinos mostly travel in the correct direction, or was it just kind of a spread where they went everywhere and you were really just, hoping that some of them statistically would make it to the MINERvA detector?
The beams at that high energy, the physics of it is that the beams are generated in a very tight beam. By the time it goes a kilometer, the beam has spread to the point where it pretty well illuminates the face of the detector, but that spreading is not a significant problem, and you know what the direction is, and that is an advantage, because if there were some neutrinos that came from a different direction, you would know that they were of different origin. They didn't come from your source.
Oh, okay. Yeah, I'm just going back to various things that I've read about neutrinos.
Yep.
And again, these are incredibly weakly interacting. I have seen neutrino detectors that are basically like enormous swimming pools filled with little light detectors. And if I understand correctly, what happens is the neutrino will come in, and every so often they will hit like a water molecule, give off a flash of light, and the detectors can measure that. But, again, there are, trillions and trillions of neutrinos coming in from the sun all of the time. So that is how rare these interactions happen, right?
Right, exactly. Now, in this experiment, we use water, but you detect them when the neutrino collides with the nucleus. And that produces a shower of charged particles that then create flashes when they interact with matter, and you can see those. So to maximize the chance of detection, you want as much mass, that is, as many nuclei as possible. And in the MINERvA detector, they have alternating layers of dense material like iron, and then a scintillator material that creates the flash of light. In that case, the total detector weighs about 170 tons. Again, the idea being you want to encounter as much mass as possible. But there are other detectors, as you mentioned, that are large containers of water, which is of course transparent. And when the neutrinos collide with water molecules, then it causes a flash, and photomultipliers around the surface of the tank then can figure out what happened. But ours is a solid detector. The MINERvA detector is solid.
Now, did the neutrino speed or the flavor oscillation, because again, from what I've read, there are something like 3 flavors of neutrinos, basically 3 different types. And if I remember correctly, they can oscillate between different types as they are traveling. Did that have any practical effect on the experiment, or was it just irrelevant based on the distance and energy?
Yes, that did not have an effect on our experiment. Neutrinos from the sun, that's a sufficient distance that you do need to take into account neutrino oscillation. But for over the kilometer or even terrestrial distances, neutrino oscillation is not expected. It wasn't a problem in ours and would not be expected to be an issue.
Oh, okay. Well, the thing that I wanted to stress for the audience that I think is probably the largest breakthrough in terms of this experiment was that you applied familiar ideas like binary encoding, synchronization, error correction, and decoding to a completely different carrier, right? Those are things that we use all the time in the electromagnetic spectrum. You applied those to something that is not electromagnetic at all, and that was a tremendous proof of concept, and it worked. That is absolutely amazing.
Yes, well, the communications theory really doesn't depend on exactly how the information is conveyed. As you mentioned, the most common ways that we communicate with digital communications is with radio waves or light, electromagnetic waves. But you can also do it with sound waves. We are not communicating digitally as we talk to each other, but we're what we could be. And so all of classical communications theory would apply if you had a sonar channel or something of that sort too. So that is a fundamental principle, that the ideas behind communications theory just assume you have some way of conveying a bit. And the physical way that you do that is immaterial, really.
Yeah, yeah. Well, and to kind of take this a little bit further, one of the things that excited me so much about this, I'm a big fan of Ray Kurzweil. One of the things that Kurzweil has written for many years is that one type of technology is inherently limited, but when we hit bottlenecks in that, right, like Moore's law, technology, market demand will drive it towards other technologies that can do the same thing. And we are seeing that with computing, right? Where it has gone from simply more transistors on a single chip. Now we're going to multi-core chips. And I've just recently done some interviews on photonics, where it is looking at, in a sense, jumping carrier, although they are both electromagnetic in nature. So what you're describing is very similar. We're taking ideas from one realm and moving them into a completely different domain, and we're still able to use those fundamental concepts.
No, I think you're exactly right. And in my experience, when you have an interface where you have two domains that haven't really talked to each other so much before, at that interface is an opportunity for doing lots of innovative things. And so in that spirit, I think when we took well-known communications theory, but applied it in an entirely new circumstance, it was an opportunity to do something interesting and to contribute.
Yeah, absolutely. And again, if I remember correctly from what I read about the experiment, I believe you guys transmitted the word neutrino, fittingly enough, using neutrinos. And the entire transmission length was much larger than the amount of rock it went through. But if I remember correctly, it was something like 240 kilometers of rock that it had to pierce.
240 meters. Sorry.
Meters. Okay.
Yeah. Yeah. So the total distance was about a kilometer between the source and detector hall, and about 240 meters was dolomite, was basically solid rock. Yeah.
Okay.
And
okay.
so again, if you're going to do straight line communication between those 2 points, no other particle would have been able to do that. No other known particle.
Yeah.
No other particle that's known to exist could have done that.
Again, an absolutely remarkable proof of concept. And I should key in on that as well. As you mentioned, it was 0.8 bits per second. So the actual speed of this is not really useful for communications, but potential applications for weakly interacting particles could include submarine communication, underground facilities, direct links through the Earth, or potentially even communication through planets, right?
Right, right. But if I could, you mentioned that we transmitted the word neutrino. There's sort of an interesting story behind that, and then I'll get back to your question about the applications. The idea of transmitting the word neutrino really came from Kevin McFarland, who was the co-spokesman of the MINERvA neutrino experiment at Fermilab and a professor of physics at University of Rochester. And his idea was motivated by the story that the first telegraph message that was sent commissioning the Baltimore-Washington telegraph line was, "What hath God wrought?" And the idea was that our message would be the answer to that question, namely neutrino. So I thought that was an interesting, but anyway, that's entirely Kevin McFarland's idea behind doing that. But yes, there are a number of potential applications. I think it's not going to beat Wi-Fi, but it is going to potentially be able to establish a reliable link where other technologies can't. I think submarine communications is probably the most compelling application. If you have a nuclear submarine at operational depth, electromagnetic waves really can't get through the seawater except at extremely low frequencies. And at those frequencies, then the bit rate is very, very slow. So typically, to communicate, the submarines have to come to a shallower depth and then float antennas. but Patrick Huber at Virginia Tech a number of years ago showed that using foreseeable technology with neutrinos, that you could have several orders of magnitude higher data rate in a one-way link to a submarine at operational depth. And part of one of the mechanisms was similar to what you mentioned, right? You're surrounded by seawater, and you use that as the target would be one way of doing it. And so you have detectors on the hull of the submarine, and they look for flashes that are associated with the neutrino collisions. But I think potentially you could have point-to-point communications anywhere on the Earth, and some extreme situations might be maybe you would like to have a channel between key points on the Earth that would still work if you had some sort of catastrophic collapse of infrastructure. Or you might want to take a little time to exchange an encryption key in a very secure fashion, and then proceed with your encryption key on a standard encrypted classical channel. It's perhaps interesting to mention that since 2015, it really came because some of our team was at NASA Glenn. Neutrino navigation has been part of the discussion of the long-range plan of technology taxonomies that could be of use to NASA. They recognize that you need significant improvements in sources and detectors, but it is recognized as potential navigation technique by NASA.
Now, could this technology be used for something like sensing or tomography as well as just traditional communications? Could you potentially use it to study the Earth's interior, or maybe look for oil reserves or various things, again, where that incredible particle penetration and weak interaction is most useful?
Yes, it turns out that in addition to generating neutrinos in particle accelerators with collisions, the most common way of creating neutrinos is in radioactive decay. They are naturally emitted in many radioactive decay processes. And so there are experiments in progress looking at so-called geoneutrinos, neutrinos that are generated from radioactive decay of elements like uranium, thorium in the Earth's core, with the idea of being, can we get some insight into how much of the Earth's core heat, originates from radioactive decay?
Oh, okay. Okay. In a strange sense, that almost takes us back to Fermilab. When you were talking about the beam divergence, one of the things that kind of popped into my mind was this idea of, okay, well, we do have these detectors like down in Antarctica looking for neutrinos. What happens if they pick up the remnants of that beam? Somebody might have to raise their hand and say, no, that one's not natural. Ignore it. That's ours,
Well, the neutrino detectors that are intended to look at galactic and or intergalactic astronomical cosmic sources of neutrinos do have the problem of wanting to distinguish between neutrinos. In addition to the Earth's, the geoneutrinos, there are neutrinos that are generated by particle collisions in the upper atmosphere. And so that's one of the reasons why the detectors are usually buried underground, so that the ground will absorb the radiation that may come from the atmosphere. In that case, you're not looking at atmospheric neutrinos. Actually, you're looking for other particles that would confuse your detector. But there are other signatures like the energy spectra, that the direction and the energy spectra are clues that you could use to distinguish between what the source of the neutrino was. Is it a geoneutrino, or did it originate from some collision in the atmosphere, or from the sun or the galaxy.
Well, again, it was absolutely amazing experiment. And that is really something that leads back to what you've mentioned at the top of the interview, axion-like particles, which may or may not exist. And it seems like that is kind of your future direction. I know you have done a ton of work. You have a lot of papers that you published on that as well. Could you kind of explain that from kind of a bird's eye level for us?
Sure. The axions, as I mentioned, it's a hypothetical particle, but it was introduced because it was realized that if the axions did exist, it would solve a puzzle, an existing puzzle in physics that they refer to as the strong CP problem. And so there was a reason to think that axions or axion-like particles might exist. If they did exist, then they would explain this particular symmetry problem that they observed. And in fact, I think the name axion, as I understand it, there used to be a detergent named Axion, and the idea was that if axions exist, they would clean up this problem in physics. But the thing that was interesting to me, as I said, was that Professor Sakivi showed that there was a coupling mechanism in the presence of a strong magnetic field that would couple axions to photons. And so that led to this idea that you could have a communication system based on photons. Maybe the beginning and the end look just like a familiar communication system. But in the middle, you convert to axions and then back again. And this has led to a series of class of experiments that are referred to as invisible light through walls experiments. They set up a cavity for an electromagnetic wave for the transmitter. And the idea is that, and you immerse that cavity in a strong magnetic field. And in that cavity, the electromagnetic wave goes back and forth many times. Each time it has a tiny probability of converting to an axion, but if it goes back and forth enough times, that enhances that probability. And if it converts to an axion, then it leaves the cavity because it doesn't interact with matter. Then at the receiving end, you have a similar machine that again you can think about virtual photons going back and forth, and every time it goes back and forth, there's a possibility that an axion will become a photon. And then at the detector end, even though they may be opaque containers or metal cavities and not even co-located, that signal would then appear in the detector. And so that's the idea about invisible light through walls, right? You have two chambers that don't have a line of sight, but yet you can convert the signal to send to one or the other. And the attraction to that is that there is a very simple way to generate photons and modulate those photons. That's well known, and the apparati that are used are much simpler. They're complicated, but much simpler than particle accelerators and 170 tons, of detector material. The question is, how sensitive can you make your detector? So, in principle, the sources and detectors could be much simpler than neutrino sources and detectors, but it all hinges on what that strength. Well, it all hinges on if they exist and what that strength of coupling might be.
Well, with axions, are there any hints that they may exist? I mean, you mentioned some experiments, and as this progresses, I think there are more ways that people will be looking for proof. I mean, do you see this as becoming something that is legitimized in science, or is it going to take quite a while before we really have a solid idea if they can exist?
Oh, the search for axions is a very legitimate idea. And as I may have mentioned at the start, it's one of the candidates for dark matter. The astronomers have noted that if they look at the dynamics of the galaxy, the things behave as if there's more mass than we can see. And
Yeah.
so the question is, what is that mass and why can't we see it? And so axions do have a small mass. It's extremely small, but if there's enough axion mass present, that could be a candidate. That, along with just the idea that it would solve this problem in physics, means that discovering whether or not they exist, it would be very interesting. Quite apart from communications applications. There aren't that many of us that are particularly interested in that application. Most of the physics community is focused on these very deep questions of, do they exist, and will they help us understand physics and the dynamics of the galaxy? So that is a very respectable continuing line of research.
Well, beyond simply neutrinos and axion-like particles, are there other particles, waves, fields, or novel physical effects that could potentially carry information where EM waves can't?
Yes. One of the ones, when my paper on axion communication appeared, shortly after it appeared, another group published a paper that basically, in so many words, said, yeah, the coupling to axions is probably going to be so weak that they won't be useful, but it might work with hidden sector photons. Now, hidden sector photons are another hypothetical particle. Unlike axions, though, the standard model allows these particles to exist, but there's no compelling argument that says if they existed, that would solve some deep mystery or understanding. Like in the case of axions, if they existed, that would explain the strong CP problem. So, or in the case of there is a reason to believe for axions to exist, hidden sector photons are allowed to exist, if you will. Now,
Yeah.
because there's some theory behind the axions, there is a theoretical prediction for what are called the QCD axions, a relationship between the coupling strength and the mass, so there's a place where to look, and it's in the case of hidden sector photons, it could be anywhere because you don't know if they exist or not. The same kind of experiment would work, and they propose the same kind of experiment. The only thing is potentially an advantage, that is, you don't need a magnetic field. In the case of the coupling between axions and photons, that was catalyzed by the presence of this strong magnetic field. In the case of hidden sector photons, there is just a coupling term that couples ordinary photons to hidden sector photons so that in principle they might convert into one another and back again. And so you could have an invisible light through walls experiment that looked just like an axion experiment, except just without a magnetic field. So if the coupling strengths were such, that could be a very attractive possibility. But again, no one knows if hidden sector photons exist.
Yeah. Well, and I should plead ignorance on that. I've heard the word hidden sector photons. I've heard people talk about that in the past, but I'm not familiar with that. Is there kind of a short description of what those are and how they might differ from a normal photon?
Well, I have to say, first of all, that I'm an engineer. I'm not a particle physicist. But my understanding is that if you look at at what is called the Lagrangian or the Hamiltonian that describes the properties of photons and hidden sector photons, they're of the same form. So hidden sector photons would look just like ordinary photons if you were in the hidden sector. But it's like this sort of parallel space where they don't interact with matter in our observed sector. Our photons interact with our matter, but their photons don't. But that's my notion of the idea. It's the dynamics look exactly the same. I think there would be a set of Maxwell's equations that would apply in the hidden sector. It's just that the sectors don't communicate with one another except through this coupling term, if it exists.
Okay, okay. That almost for my mind, the idea that's kind of coming to mind is they may exist in almost like a separate manifold, right? I know that's probably not the best way to describe it, but now I also wanted to ask about quantum effects. Have you explored quantum tunneling, entanglement, non-local correlations, or other quantum field phenomena as potentially either being elements of a communication system, right? They could be parts that interact with something using neutrinos, axions, or hidden sector photons, or just in its own right?
Well, I have not personally. I have had some work on quantum computing, which of course uses some of the same concepts of entanglement. Um, there is work and there are some ideas about using qubits as very simple, very sensitive detectors of particles, potential particles like neutrinos and axions. The qubits in quantum computing, of course, are very sensitive. In fact, in the early days of quantum computing, you might hear someone joke about a bad quantum computing. A bad quantum computer was an excellent sensor because the qubit state was destroyed by interacting with the environment. And the whole name of the game is to try to isolate the qubit from the environment so you can maintain the quantum information for computing. And so there are some very interesting ideas about using the technology that's being developed to make high quality qubits and use those for particle sensors. There's another touch point between quantum and the information theory, and that is there is an area, there are some modifications to classical information theory that you need in the quantum context. So there is a quantum information theory. I don't think that will lead to any major increase in speed or capability of networks, but I think quantum networks will play an important role from at least two or three perspectives. One is security, because photons in the quantum sense, if you intercept or mess with one of them, then there's no way you can do it without somebody else knowing that you've messed with it, right? So that you can't eavesdrop on someone without them knowing it, and that is the whole idea behind quantum key distribution. But there's another context, and that is distributing entangled photons across a network. And this might be to couple two quantum computers so that you have parallel or quantum computers in multiple places all solving the same problem, but they have to be able to exchange a coherent entangled state. Or there are some types of sensors that enhance their sensitivity by having geographically displaced entangled photons as well. So I think that those are two touch points. I think using qubits as a sensor themselves, and then using quantum networks to distribute entangled photons for quantum computing and sensing applications.
Oh, interesting, interesting. Well, and this is a little bit of an aside from our core topic, but I've just recently done a couple of interviews related to photonics, and that's an area I know it has been. It's kind of like fusion research, right? It's like it's almost 20 years away, and it has been for the last 20 years. But photonics is used in existing communications technology. That's what makes it so exciting. So. One of those, a company is actually pushing forward with photonic CPUs, right? And there are other companies, I'm sure you followed this as well, that are looking at accelerators that are all photonic based. And there's this part of me that wonders maybe they could tap into this, or like as you mentioned, maybe there could be some kind of a communication between what's happening in the photonic level and axions, so it's intriguing.
Absolutely. I think many of those photonic computers are, I think am aware of the one that you're talking
Yeah.
about, is, if I'm correct, is basically classical. But optical computing has been of interest, as you point out, for many years. And the advantage has been you can do all this parallel computation with a two-dimensional light beam, and how that light beam um, is controlled and evolves. The bottleneck has always been getting it into and out of the electronic domain. And I think one of the differences in these um, latest approaches is that they have schemes for getting information without getting the answer without having to have those conversions, or by minimizing those conversions. But I think the idea of adding a quantum dimension is probably a different animal. I mean, clearly there are some overlaps, and there are all optical quantum computers in addition that people are constructing, where the photon itself is the qubit. But I think and there are some common components, right? Because lenses, wave plates, these waveguides, mirrors, all these things are basic components that you would use in any such system. But I think that from the architecture point of view, they would be different animals. As I said earlier, you always run into interesting things when two areas touch, and so who knows what the opportunities might be there.
Absolutely. Absolutely. And I should apologize for throwing kind of twists and turns and a monkey wrench in there, because I could see this is an incredibly complex technical topic, and you have absolutely the education, expertise, and pedigree to be able to discuss it. But it's difficult to put things like that in very simplistic terms for a short interview. So thank you for that. And let me thank you so much for your time today as well. I want to close by asking, what is coming up next for yourself and your work and this novel communications that you've explored in the past?
Well, I think the next step for neutrino communications would be to think through how you would build a source and detector, a system that was designed for communications rather than particle physics. I think to make things practical, you really have to have some breakthroughs. There needs to be physical breakthroughs in our understanding of how to generate neutrinos, as well as how to detect them. But as a starting point, what we did was we took a system that was designed for a particle physics experiment and used it for something for which it wasn't designed. If you started off and said, okay, I'm going to design a neutrino source in a detector specifically for the purpose of a communication system, how would it differ? How would it look? One of the potential ways where you might have a difference is that in the MINERvA experiment, the entire detector was about 170 tons of material. But really the physics part was about 4.7 tons in the middle, where they were looking for interactions that happened in that space. What they could see and trace all of the collision products and so forth, and understand the physics. But for a communications point of view, we just wanted to see anything that could plausibly be associated with the detection of a neutrino. So, we mentioned that the neutrinos were coming through that rock, hundreds of meters of rock. And so there were collisions in that rock that created showers of muons, which then entered the detector. So it's as if the mass of the detector had been greatly expanded, because we were using the rock in front of it as part of the detector. And by counting those so-called rock muons, we were able to increase the the particle count, the sensitivity, by about an order of magnitude. Instead of 0.8 events per beam, it would be about a tenth of that. And so we did. I mean, that would not be something you do for a particle physics detector. And it might suggest how you make it less expensive too. If you don't have to build the detector, if you just use, surrounding rock or mass, sort of like in the sea with the submarine. So I think that the next logical step, and I'm giving some thought to that, next logical step is with known physics, we need breakthroughs, but with known physics, let's see if we were going to design a system that that was specifically intended for communication and not for particle physics. What would that look like? There is a very interesting analogy that I like to think about in the history of electromagnetics. So Heinrich Hertz demonstrated electromagnetic waves. I think he had in 1887, he had a tabletop experiment that showed that you could that these electromagnetic waves were generated at one point and then detected at another. And he has this very interesting quote that I'll read here. His assessment of this was, it's of no use whatsoever. This is just an experiment that proves Maestro Maxwell was right. We just have these mysterious electromagnetic waves that we cannot see with the naked eye, but they are there. And of course, in 1887, we didn't know about crystal detectors. We didn't know about vacuum tubes. We didn't know transistors. We didn't know about quantum mechanics. And based on what was known in 1887, his assessment was there's no practical use of these electromagnetic waves. But, a century or so later, the situation is very different. It's always difficult to predict the future, as they say. But if there is some physics out there that we haven't discovered, that may make the difference in making neutrinos a practical channel for communications. But we just have to wait and see.
Well, again, it's absolutely remarkable. The work that you have done is absolutely, I'm gushing over this. It is so tremendous. And this is an enormous breakthrough. I'm going to put links in the YouTube show notes. I want people to visit that and learn more about your work, learn about axions, learn about sending a signal with neutrinos, and kind of see where you've been taking things from a physics perspective. And for today, let me thank you again so much for your time, sir.
My pleasure, Tim.